Good morning, everyone. Today we would like to present to you our work on smart diagnostic algorithms for automated detection of childhood pneumonia in resource-constrained settings. This is research we have been conducting at the University of Oxford in the UK. This presentation will contain the following elements: an introduction of the problem and outstanding challenges, an overview of the methodology we use to address these challenges, a summary of our key results, as well as a brief mention of our next steps. Childhood pneumonia is the main cause of mortality amongst young children, killing more children under the age of 5 than HIV, malaria and TB combined. Annually, this equates to more than 1.1 million children's lives lost. 95% of pneumonia cases and 99% of subsequent mortality occur in resource-constrained settings. So what is the reason for this disparity? In resource-rich settings, childhood pneumonia is typically diagnosed by a well-trained clinician using advanced diagnostic tools such as chest X-rays and blood tests. In resource-constrained settings, the situation is different. The closest hospital is 2 hours away. The local health worker only has access to basic diagnostic tools and often struggles to differentiate pneumonia from other diseases. Appropriate diagnosis has been shown to reduce mortality by as much as 42%. However, to make evidence-based decisions on treatment, information of various aspects of the disease is essential. Presence of pneumonia, its severity, as well as its etiology. Is it bacterial or is it viral? The current mode of diagnostics is very resource-intensive, both in terms of expensive medical equipment as well as medical expertise. Thresholding of individual clinical characteristics has been attempted in the past, with no individual clinical characteristic delivering acceptable performance. Similarly, the WHO has developed a set of guidelines, IMCI, to streamline the diagnostic process. However, studies have reported huge inter- and intra-observer variability as well as poor specificity, leading to inappropriate administration of antibiotics. So this is where smart engineering can come to the rescue and develop a set of robust, quantifiable, affordable and automated tools for diagnosis. As highlighted before, pneumonia presents a multifaceted diagnostic challenge. This can be visualized through 3 separate diagnostic axes. Each axis describes a diagnostic challenge that should be addressed to best inform treatment. The research presented here focuses on the main challenge of identifying pneumonia. The data analyzed was acquired during a clinical study in the Gambia. The participants were children between 2 and 59 months old who either suffered from pneumonia or were recruited as controls. More than 60 clinical features were measured on each child. Our task was to leverage machine learning tools to design an analytical pipeline that eventually delivers algorithms for automated diagnosis of childhood pneumonia, using a limited number of clinical characteristics that can be captured both affordably and quantifiably in resource-constrained settings. So consequently, we applied a variety of pre-processing, feature selection, and classification techniques that are listed here. So for example, you can see that in terms of feature selection, we applied a majority voting approach that fuses 7 different feature selection techniques. In terms of the classifiers, we investigated the performance of logistic regression, support vector machines, as well as random forests. So let's have a look at some of the results. The feature selection narrowed down the feature set to the 5 features listed here. It should be noted that 3 of these features, namely respiratory rate, heart rate and oxygen saturation, can be captured through the same pulse oximeter measurement. Next, the use of 3 classifiers is visualized via the ROC curves. A closer look revealed that the somewhat superior results obtained via random forests. Namely, with 4 features, we were able to achieve sensitivity and specificity greater than 97%. A dimensionality reduction technique called TSNE was used to visualize the multidimensional data into 2D. You can see from the plot that the 2 classes of pneumonia and controls are well separated in space, apart from a few misclassifications. So for those of you who wonder how TSNE works, details can be found in the original paper by van der Maarten, but here is an intuitive summary. TSNE, or T-stochastic neighborhood embedding, aims to capture both the local and global structure of the data by assuming that similarities between points in high dimensions should be preserved in low dimensions. Mathematically, Euclidean distances are converted into a set of conditional probabilities, and the differences between the high and low dimensional equivalents are minimized. Since the GHTC submission, we have also investigated the additional 2 diagnostic challenges, severity and etiology of pneumonia, using data from the same clinical study. Following a similar analytical approach, we were able to determine both the severity and the etiology of pneumonia with high sensitivity and specificity. However, unlike the identification problem, these 2 problems require the inclusion of biomarkers such as C-reactive protein for severity and lipocalin for etiology determination. The available dataset had some associated limitations, such as the lack of disease progression information and the fact that all controls were entirely healthy. Nevertheless, this preliminary work suggests that machine learning tools can be successfully leveraged, combining quantifiable measurements to deliver automated, multifaceted diagnosis of pneumonia. The performance of such an approach was seen to be superior to the one of the IMCI guidelines. Moreover, this could offer an alternative to the traditional use of chest X-rays in settings where these are simply inaccessible. So finally, if you think of our machine learning algorithms as the brain of a mobile health diagnostic tool, our next focus is equipping the tool with limbs that would enable the robust and affordable measurement of the pre-identified features. Namely, we're extracting 3 of the features, oxygen saturation, heart rate and respiratory rate, from a single measurement via a pulse oximeter. We are currently investigating options for automated detection of lung sounds and are very eager to connect with other teams with expertise in the field. Finally, we would like to acknowledge the support of our funders, and we're extremely grateful to the GHTC organizers for allowing us to deliver this presentation remotely. Please reach out if you have questions and suggestions, or if you would like to discuss potential collaborations. Thank you very much for your attention.